Okay, so yesterday we looked at, or last video I should say, we looked at arithmetic sequences, numbers, or sorry, a list of numbers that are have a common difference between them. And today we're looking at what's called an arithmetic series. So kind of really this is the same thing, except for what you're doing now is you're adding all the terms or summing them between. So if we think about, maybe I'll just write up here a pattern number. So like 2 plus 5 plus 8 plus 11. That would differ from a sequence, which would just be 2 comma 5 comma 8 comma 11. But they would be the same, and they're both arithmetic. That is the difference between each consecutive term is 3 here. They both have 4 terms in them, and their term numbers would be the same. So the term 1 would be 2 here, and term 1 over here would be 2. So a lot of similarities here. So the only difference here is that in a series you're actually adding the numbers together. So we have 2 plus 8, which is 10, plus 11, which is 21, plus 5, which is 26. So this should sum to 26 when we're done. Whereas in the sequence, they don't sum to anything because it's just a list of numbers. There's not telling you to do anything with those numbers. So if we denote Sn to be the sum of the first n terms, then we would get a being the first term, then a plus d, a plus 2d, a plus 3d. And then we have this weird thing on the end, which actually is the Tn formula we learned yesterday. So this would be the first term plus n minus 1 multiplied by d. So if you're not sure about that formula, you should really watch the video before this one to understand that. So this is really going to be our last term in our pattern here. And so we're trying to figure out how can we write a formula that would allow us to do that, to determine the sum of all the terms in an arithmetic series. So this is just a little bit of, not sure if it's factual information on, but there is a story that says Gauss, who's a famous mathematician, was sent into the hall by his teacher to add the numbers from 1 to 100. And didn't have calculators back then, so it wasn't a matter of just adding 1 plus 2 on the calculator and then plus 3 and plus 4. And so he came up with a pretty clever way to do this pretty quickly. In fact, he was done probably within about 2 minutes without the use of a calculator. And so what he looked at was the pattern of numbers, which would be 1 plus 2 plus 3 plus 4, and then just keep adding all the way up to 99 plus 100. And then he thought if he reversed the pattern and counted backwards, add it from basically 100 to 1, and then just kind of staggered the puzzle this way. So 99 plus 98 plus 97 plus 96 plus, and then all the way to plus 1. And then he, instead of summing them horizontally but vertically, what you wind up getting is 100 if you add the 2 rows, and then another 100, and then another 100, and then another 100, another 100, and you get 100, and the last 100. And so basically there's a whole bunch of hundreds here, but how many hundreds are there here? So the first row shows 100 numbers, and then you have this extra number here. So there's actually 101 hundredths. And so he said, well, if I take 101 hundredths and times them together, I just have to add 2 zeros here. So I'd have 10,100. But what I've really done is I've added this twice. So let's divide this by 2. And so this would be 5,050. And it was pretty neat. But he did this when he was 8, so that's even more neat. But anyway, so if we go back to this problem, what we could look at is our terms here, and we're going to find the sum, Sn, of these terms, and I'm going to count it backwards here. But instead of writing the last term this way, I'm just going to call it L, if that's okay. So we'd have the last term, and then we would be taking L, and be minusing the common difference, and the last term and minusing 2 common differences. Keep putting commas here, sorry about that. And then we'd be adding the last term minus 3 common differences. And then we would get all the way down to our first term here. So if we subtract these now, actually, let's add them. Let's add these two terms. We're going to add this Sn to this Sn. So that's going to give us 2 Sn's. And then we're going to get equals A plus L. And that's when we add A plus L. And now if we add these, that would be A plus L, and the D's would cancel. So we go brackets around that, plus another A plus L. And then we do it again with this, and we're going to get another A plus L. And we're just going to keep on doing this. We're going to get a whole bunch of A plus L's here. And even the very last term, we're going to get A plus L, because we're going to have that L plus that A. So at the very end, we're going to have another A plus L. So what we're going to get is 2 Sn, so the sum of the series twice, kind of what Gauss did, and that would be equal to A plus L. But look at all the A plus L's you'd have. You'd have 1, 2, 3, 4, all the way up to n. So multiply this by however many terms there are in the pattern. And so the sum of the n terms here would be n divided by 2, A plus L. And so that formula is quite useful if you know the n value. So you have to know the n value, the A value, and the L value. But it would assume you don't know the D value. So if you didn't know what D was, so let's say that was not told to you, then it'd be a really good formula to use for an arithmetic series. If we sort of unscramble the L part, though, we get n over 2 multiplied by A plus L. And don't forget, this actually is L here. So this would be A times n minus 1 times D. So Sn would equal n over 2 multiplied by 2 A's plus, oopsie, I wrote that wrong actually. Sorry, let's get rid of this thing here. That's A plus n minus 1 D. So we have 2 A's plus n minus 1 D. And that formula would be really useful if you knew the n and the A and the D values. So if you knew A, N, and D, and it would assume that you don't need to know the last term in the pattern. So we've kind of got 2 different formulas depending on what information is given to you, but they both determine the same thing, the sum of the n number of terms in an arithmetic series. So if we go to the first question here, let's say we're being asked to add all the numbers from 1 to 1,000 now, so a bit more challenging than what Gauss did, but I guess you could use this Gaussian approach. But what do we know here? Well, in this question, we know that the A value is 1, so we know A is 1. We know that the common difference, we're basically adding 1 every time, so a common difference of 1. Numbers from 1 to 1,000 would have 1,000 terms. And we know that the last term is also 1,000. So you could really use any of the formulas, or either of the formulas, and I'm going to choose maybe the easier one to work with, which would be the sum of the n terms is n over 2 multiplied by A plus L. So if I plug my numbers in for this, I'm going to be finding the sum of the first 1,000 terms, which would be an n value of 1,000 divided by 2 multiplied by my first term of 1 plus my last term of 1,000. And so if I work this out, I'm going to get 500 multiplied by 1,001. And if I work that out, so 1,001, see, 1,001 plus, oopsie, times 1,001 times 500. And that should give me 500,500. I've done that right. Okay, so moving on to the next question. We're given a series here, 7 plus 10 plus 13 plus all the way to 100, and find the first 25 terms. Well, If you look at the difference between 10 and 7, that's 3, and 13 and 10, that's 3. So we do have an arithmetic series here. So we know the a value is 7. We